Okay, so today we have quite a special treat. We are going to be integrating this function here in a very special way. This is very easy to evaluate. It's extremely easy to evaluate. But let's evaluate it in a harder way, just to practice these harder techniques. Okay? So I'm going to let f of z equal to z squared, and I'm going to draw an argand diagram. The real axis and the imaginary axis right there, and what we essentially have is a contour, a nice semicircle contour, and this is what it would normally look like, but right here we've got these bounds. This has to be 2 and this has to be -1. So in fact what we need to do is set the points -1 and 2. What's the midpoint? It's 1/2, meaning the radius of this circle is going to be 3/2, 3/2. So it's going to be a circle looking like this, with its maximum point here. It's going to come back like that. We'll call this top curve here, this line, gamma. And you see what we have here, this closed contour integral over c of z squared dz. There are no singularities in here, thus no residues. So we can evaluate this to 0 because no singularities by Cauchy's residue theorem. But let's continue. We got that this is actually equal to the integral from -1 to 2 of x squared dx, which is exactly what we wanted to evaluate, but plus a second line integral over gamma of z squared dz. So these two added together are 0. So whatever this must be, this is the negative version of that. So let's continue. We need to parameterize this curve gamma here somehow. So we're going to let small gamma of t parameterize gamma such that t is between 0 and pi. Gamma of t, well, it needs to be in the form e to the I theta plus 1/2. So it must be 1/2 plus 3/2 e to the I t. We need to work out gamma, whoops, we need to work out gamma prime of t, which is just 3i over 2 e to the it. And then we can plug this in, and we get that the integral from 0 to 2 pi, actually, let's write this fully first. The integral of gamma of z squared dz is equal to the integral from 0 to pi of gamma t squared multiplied by gamma prime of t dt, which is nothing other than the integral from 0 to pi of 1/2 plus 3/2 e to the it squared times 3 halves I e to the it dt. And let's bring this constant out to the front. We get 3I over 2 times the integral from 0 to pi of, and we can factor out a half from here, so 1/2 squared, factor that out. 1 plus 3 e to the it squared dt, which is nothing other than 3I over 8 times the integral from 0 to pi of e to the it multiplied by this. If we just expand out, it's 1 plus 6 e to the it plus 9 e to the 2 it dt, which is easy to evaluate. 3I over 8 times the integral from 0 to pi e to the it plus 6 e to the 2 it plus 9 e to the 3 it, and we're getting close now, dt. So this is just 3I over 8 times e to the it over I plus, if we drag this constant down, we get 3 e to the it over I. Same thing here, we get another 3 e to the it. Sorry, I've been forgetting these constants. 2, 3 over I, evaluated from 0 to pi. Okay, so we can factor an I from the bottom here. These are going to cancel. We get 3/8 times, okay, cancel, 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 cancel. So we get e to the I pi is -1. 3 times e to the 2 I pi is just +3. And this is -3. Minus e to the I0 is just 1 plus 3 plus 3. Okay, which is 3/8 times -1 minus 7, which is 3 over 8 times -8, which is just -3. So we get that this original integral here is just equal to -3. So the integral from -1 to 2, let's do it in a different colour. The integral from -1 to 2 of x squared dx minus 3 is 0. Therefore, the integral from -1 to 2 of x squared dx is 3. And there we go. We get the exact same answer as if we would have done from normal integration. The only difference is you get to show off. This really doesn't provide any practical utility for this example, but for harder examples, it's a very useful tool. But I hope this has helped you to understand complex contour integration. I didn't really explain much about the singularities because there were none in this example, but I think it's always good to start off with the easy examples and then work your way up to even harder ones. But I hope you enjoyed.